Welcome, fellow chemists, to the 8th video in the Instrumental Analysis series. This is half IR, half Mass Spec, and includes 4 of the toughest problems I have ever posted. Well, tough that is, unless you have watched the previous 7 videos. Speaking of previous videos, here are the references to specific bond types and the frequency of the peaks that represent the stretch or bend. I did add the NH bend as well. When the IR spectrum is on the screen, pause and analyze it. Same goes when the Mass Spec is up, where I'll give the M-peak data if available. Go back and forth as many times as necessary. I will put a warning on the screen before going over the answer. Any modifications to the spectrum are done to make things easier for you to see. Without any further ado, let's get to the first problem. Coming off of all the IR analysis we have done recently, you definitely pin down this peak on the far left as that of an alcohol. The peaks next door indicate a lot of hydrogens bonded to sp3 carbons. This gets confirmed around 1500 with the sp3 bending peaks and with the CH3 methyl peak next to it. We find around 1050 the carbon-oxygen single bond peak. What we can be sure of now is there is an alcohol on an alkane because there is no evidence of sp or sp2 carbons. On to the mass spec where there is no obvious M peak. We can use 2 features to infer what the mass of the molecule probably is, though. First, the spectrum stops at 90. This is unlikely to be the actual M peak, but it gives us a starting point. Second, we are confident this is an alcohol, and they are known for a fragmentation that results in the loss of a water molecule. If they lose a water molecule, there should be a peak 18 units below the M peak. There are 3 candidates for this, with one literally sticking out above the rest. By the height, we can infer this fragment is produced a lot. It also has a mass of 70, which means the M value is likely 88. Now, another simple fragmentation on an alcohol is the alpha cleavage, where the carbon-carbon bond next to the alcohol breaks. If the alcohol is primary when that bond breaks, the fragment is mass 31, and we find a very noticeable peak at 31. So to recap what we know now, the molecule is a primary alcohol composed of sp3 carbons, has at least one CH3 on it, and has a mass of 88. Time to start drawing potential candidates. And there are 4 of them. We can choose the correct one if we remember what happens when these molecules lose a water. The second hydrogen necessary to form water comes from the third, or gamma carbon, after the alcohol group. For simplicity, if there is more than one option, I pick the location which, after the hydrogen is taken, produces the most stable fragment. Because when the loss of water occurs, the cation produced is also a radical. The more stable the radical, the more likely it will be produced. The top left structure produces a secondary radical. Since the top right produces a primary radical, it can be ruled out. The bottom left produces a tertiary radical, which means we can forget about the one above it now. As for the bottom right, it produces a secondary radical. So this molecule on the bottom left with the hydrogen and OH put back is the molecule that produced both spectra, 3-methyl-butan-1-ol. Let's move on to the next one. This IR spectrum is missing the alcohol that the previous one did, but it does have the peaks representing the hydrogens on sp3 carbons. Unlike the previous one, there is a definite carbonyl or carbon-oxygen double bond. We find the bending vibrations for the sp3 carbons as well as the CH3s. The peak around 1200 tells us we have a carbon-oxygen single bond. Let's see what we can learn from the mass spec. And thank goodness there is a molecular ion peak at 102 as well as the M+1 peak at 103. Doing the fancy math with those intensities, we get the number of carbons as 5. We could mess around with the possible structures, but the base peak is 29, and a likely structure for that is C2H5. It is produced a lot, which could indicate there are multiple ways to break the molecule into this structure. Given there is a carbonyl and a carbon-oxygen single bond, an ester is a possible structural candidate. This structure has one of our 5 carbons and a mass of 44. That leaves 58 units of mass unaccounted for, and the C2H5 structure is mass 29. If there are 2 of them, that makes 58. If we put C2H5 on either side of the ester, we have our molecule, ethyl propionate. This IR with the set of peaks on the far left has the telltale sign of NH bonds. There are hydrogens on sp3 carbons again. The peak between 17 and 1600 is really intense, so it is likely a carbonyl. We see the usual peaks that show the presence of sp3 carbons and CH3. The peak just above 1100 could be a carbon-oxygen or carbon-nitrogen single bond. We are pretty certain there is a carbonyl, but the nitrogen has to bond somewhere, so assuming this represents the carbon-nitrogen bond is sensible. We may need to go back and change this assumption, but let's move on to the mass spec. The M peak is at 73, which confirms we have a single nitrogen on the molecule. That also means we can ignore the intensities, as it may not give us the correct number of carbons. The base peak is 44, and for messing around with potential structures of that mass, you should have come up with the ami. That leaves 29 mass units left over, which happens to be the third largest peak, and the best fit for that remaining mass is the structure from the previous substance, C2H5. The amide structure has a carbon bonded 3 times, and if the C2H5 is placed there to give it the fourth bond, we have arrived at our answer, propionamide. Now on to the final problem. This certainly is a different IR, and perhaps easier to read because of how little sticks out. Anyway, we definitely find our good friends the hydrogens on sp3 carbons. And about the only other thing we see here is the other peak indicating there are sp3 carbons, but curiously it's missing the peak for CH3. Might as well move to the mass spec where there are a trio of M peaks with the M peak itself located at 118. The number of carbons can be calculated using the intensities from the first two. It turns out there are 6 carbons, and now we no longer need the M plus 1 intensity. The M and M plus 2 peaks are in a roughly 3:1 ratio, which is observed if chlorine is on the molecule. So there are 6 sp3 carbons, no CH3s, and a chlorine. Do you have the structure? Here is a hint if you need it. This peak at 83 is what happens when the chlorine is taken off. Can you develop a 6 sp3 carbon but no CH3 structure with mass 83? Hopefully you figured it out by now that the identity of the fourth and final substance is chlorocyclohexane. And with that final problem complete, it is time for me to wrap up the instrumental analysis series for now. Yes, NMR is still on the distant horizon, though I will start sooner than I anticipate. If anyone can put in the comments in what year the picture suggests, I will get around to it. However, even if none of you can figure it out, I'll probably do it anyway because someone helped me simulate the spectra and it's a lot of fun to mess around with. But all that is a story for another day, and until it is told, thank you very much for watching. I have no idea what my next video will cover, but feel free to put requests or questions on this video in the comments below.